So wrapping up on our discussion about rational functions before we actually get to graphing them, which is sort of, again, the ultimate goal of rational functions is sketching a graph. We have one more little question to ask and to answer, which is, do we cross our horizontal asymptotes? So to this point, we know how to find intercepts. That's the same as any function in the world. We've talked about vertical asymptotes, where the denominator is 0. We talked about removable discontinuities, where the numerator and the denominator are 0, sort of the weird case where we end up with a hole in the graph. We've talked about how to find horizontal asymptotes, but we didn't quite get to the part where we ask if we cross the horizontal asymptote or not. So just to kind of give us a quick recap of some of the stuff we were going to talk about, requires that we sort of review this real quick. Horizontal asymptotes boiled down to this little mnemonic that we came up with at the end of the day. I guess it would have been Friday. Bobbio botno eats DC, right? And Bobbio stands for if it's bigger on the bottom, y equals 0 is your horizontal asymptote. Bigger meaning the degree of the polynomial, right? So bigger on bottom is y equals 0. Botno means bigger on top. There is no horizontal asymptote. The graph's end behavior kind of goes off to infinity or negative infinity, right? And then eats DC stands for exponents are the same, divide coefficients. So if it's the same sort of degree on top and the bottom, if it's like x cubed over x cubed, then you just divide that first term's coefficient. And all this kind of comes from what we used end behavior models, right? Where we just sort of looked at what term's most important for really big values of x and really small values of x, and then we did some arithmetic on that, right? Because remember, horizontal asymptotes are basically asking what happens to my graph for infinitely large x or infinitely small x. Okay, so just to kind of look at an example with, oh wait, I guess I'm not doing the example just yet. We'll do an example in just a minute where I kind of do this. But this was sort of the end result of the horizontal asymptote discussion that we had in the previous lecture, right? So the problem with horizontal asymptotes is they're a little bit weird compared to vertical asymptotes. Vertical asymptotes can never be crossed, and that makes sense because otherwise it wouldn't be a function, right? But you can actually cross a horizontal asymptote, and there are several cases in the world where you cross a horizontal asymptote. You can cross it once, twice, 50 times. There are some functions that cross horizontal asymptotes infinitely many times, right? So you can actually cross horizontal asymptotes. All that is required to say something is an asymptote is as x gets infinitely large or small, so as I get very, very big values of x or very, very small values of x, the y values get arbitrarily close to the asymptote. That's what an asymptote is, right? So it doesn't have to necessarily avoid crossing the asymptote. It can cross it. It's just as the x values get very, very large or very, very small, the y values get arbitrarily close, right? So we kind of have an idea of, like we can imagine a graph of what that means, okay? But there's nothing said here about the normal-sized values of x. So any x equals a number, anything could happen, right? I could get that y value of the horizontal asymptote, and that's perfectly fine. Okay, so it's sort of a weird situation where we can cross the horizontal asymptote. So the question is, how do we know? How do we know if we cross it or not? And probably an extra question that I didn't type here, but a good one that is also worth considering, where do I cross it, right? So if I cross the horizontal asymptote, at what x value do I cross it, right? And all of this information would certainly be valuable if we were to try to draw a graph of a rational function, right? So we have to figure out how to answer this question, and once we know this one, we got everything we need. Okay, so now let's look at an example of a function. So say we have something like this. Okay, this is clearly an eats DC situation. Exponents are the same, so you divide coefficients. But if you don't like the mnemonic, because it's a little dumb, you can just make an end behavior model real quick. And the end behavior model in this case, of these three terms, the 2x squared is the most dominant term. And of these two terms, the x squared is the most dominant term. So for very large values of x, this function and this function are approximately the same thing, right? 2x squared over x squared and this whole mess are approximately the same. So they behave similar for very large and very small values of x. Well, obviously the x squareds cancel and you end up with just 2. So your horizontal asymptote is y equals 2. Now you could do all this work, or you could just kind of look at it and go like, yep, exponents are the same, so y equals 2 is my horizontal asymptote. Either way is fine. Okay. Now, so that's how we find the horizontal asymptote, right? And that's mostly review. But how do I know if I cross it, right? So I know the horizontal asymptote is y equals 2. Well, here's a picture of the graph, and clearly I do cross the horizontal asymptote, right? The green line is the horizontal asymptote, and you can see as x gets very, very large, 10, 20, 30, all the way up to infinity, this distance between the curve and the graph is arbitrarily small. And when x gets very, very small, same Same thing, right? The y value gets very, very close to the horizontal asymptote. But right here, you can see there's a point right there where my graph, my red graph, the curve that I'm actually drawing, f of x, actually crosses the horizontal asymptote. So how do I know that's going to happen just from looking at the equation? Because remember, the goal is to draw the graph. So obviously, if we're looking at the graph, we can see that it does. But how do we get the picture of this graph? How do we know that we're going to cross, and more specifically, how do we know where we're going to cross? Like, what's the x-coordinate of that point? The y-coordinate's 2, right? Because it's on the line y equals 2. But how do I know the x-coordinate? Okay. And it turns out, like, mathematically, it's not that complicated of a thing. It sort of makes good intuitive sense. If we cross the horizontal asymptote, that means y is equal to 2, right? I mean, that's literally what's happening right here. This is y equals 2, that green line, and then this is f of x. So if I cross the horizontal asymptote, that means my y value is equal to 2. So if I just set f of x equal to 2 and see if I can find a value of x, that will tell me if I cross or not. If I find a value of x, that means I cross, and I cross at that value of x. If I can't find a value of x, if I end up with a no solution, which would be like if it says, like 1 equals 0 or something like that, then I know I don't cross at all. Okay, so let's take a look at this example. Again, we know it crosses, but let's see if we can figure out how we can show that mathematically. So I took my function f of x, and I set it equal to my horizontal asymptote, x equals 2. And now I have a rational equation. Well, I know to solve this equation, I can multiply both sides by the denominator. That will kill the denominator on the left side and just leave me with the numerator, right? And then 2 times x squared minus 4 gives me 2x squared minus 8. Now, if I subtract 2x squared from both sides, those will cancel out, and I'll be left with just negative 6x minus 4 over here and negative 8 over here. I added 4 to both sides because I kind of skipped a step, right? So I subtracted 2x squared from both sides, and I added 4 to both sides. And then if I divide both sides by negative 6, I get x equals 2/3. So what does this actually mean for me? What does this tell me about my graph? Well, not only do I now know that my graph crosses the x-axis, or I'm sorry, my graph crosses the horizontal asymptote, I know specifically where it crosses. It crosses the horizontal asymptote at x equals 2/3. So now I could actually plot that point if I were to draw my graph. When x is equal to 2/3, y is equal to 2. That's also the only place where I crossed my horizontal asymptote, right? If there were more, I would have found more values of x. So I know I crossed the horizontal asymptote exactly once, and it's at x equals 2/3. Again, because I got a value for x, that's how I know it crosses. If everything here canceled out and I just ended up with two numbers that weren't equal to each other, that's how I would know there was no cross of the horizontal asymptote, okay? Those tend to be the less interesting cases, but they do show up every once in a while where you just don't cross it whatsoever, okay? Kind of the simpler versions. Okay, let's look at another example, but I want to sort of go through the full stack of everything that I would have you do before you attempted to graph a rational function. And then first thing tomorrow, we'll actually graph this one to show you that with the information that we already know how to get, we can draw a nice, pretty graph, rough sketch of any rational function. Okay, so let's start with this. This is my function. So I got 3x squared plus 2 over x squared plus 4x minus 5. Let's start with the intercepts. This is like weeks ago, well, a week ago, last week, Tuesday, I think. We talked about how to find intercepts, but it's the same as intercepts for any function in the entire world. If I want the y-intercept, I set x equal to 0, which just means plugging in 0. I get 2 on top and negative 5 on the bottom, so negative 2/5. Easy enough. Okay. If I want the x-intercept, I set y equal to 0, so I set my whole function equal to 0, and now I'm just solving a rational equation. I multiply both sides by the denominator. Well, 0 times anything is 0, so I'm really just looking for where the numerator is equal to 0, right? And then that will give me my x-intercept. Maybe, unless I have a removable discontinuity, but we'll get there in a second. And then I solve this. So I subtract 2 and I divide by 3, and I get x squared equals negative 2/3. Well, if I take the square root of both sides, I'm going to get an undefined answer, so no intercept, right? This is an imaginary number, the square root of negative 2/3. So now I know two things about my graph. I know it crosses the y-axis at negative 2/5, and it never crosses the x-axis. Okay, so no matter what, this function will never touch the x-axis. That takes care of intercepts. The other thing we have to look at is asymptotes. So let's start with vertical asymptotes, which was the first version that we learned. Remember, a vertical asymptote occurs when a rational function is undefined, when it's a something over 0. So if I set that denominator equal to 0, that's what's going to cause my function to shoot off to infinity as a y value, or down to negative infinity possibly, right? So let's just set the denominator equal to 0. So I have x squared plus 4x minus 5 equals 0. That's a quadratic, so let's factor it. I have x plus 5 times x minus 1. Right? And you can double check to make sure that that's what it factors into. So I see two vertical asymptotes, one at x equals 1 and one at x equals negative 5 by the zero product property. Okay, so now we found both the y-intercept and there is no x-intercept, right? So we've done both intercepts. We've also talked about where the vertical asymptotes are. We need to take a pause for a second to check to make sure there's not any removable discontinuities. Remember, sometimes we find vertical asymptotes that are actually removable discontinuities, and that's when the numerator and the denominator are both equal to 0, because 0 over 0 is very different from number over 0, right? We kind of talked about that last week on, I want to say, Thursday. Yeah, I think Thursday. So removable discontinuities, there's none in this case. The numerator can't be 0. We already checked that when we did the x-intercept, right? So typically if you have an intercept, an x-intercept, and a vertical asymptote that match, that's a removable discontinuity. And then you have to do some work with that. But in this case, there isn't one, so we don't have to worry about removable discontinuities, which is great. As far as horizontal asymptotes go, this is an Eats DC, so this end behavior model, EBM, end behavior model, is just going to be 3x squared for the top and x squared for the bottom. The x squareds will cancel and you'll end up with y equals 3. Okay, so all of this is the stuff that we did last week to sort of summarize the stuff that we know about this rational function so far. So I put it all sort of in one big list over here. We know the y-intercept is -2/5. There's no x-intercept. We have two vertical asymptotes at x equals 1 and x equals -5. No removable discontinuities because there's no way to make this function look like 0 over 0. No x value that would make both the top and the bottom 0. And my horizontal asymptote is y equals 3. So I've done every sort of piece of analysis I need to draw this graph with one exception. I have to see if my function crosses my horizontal asymptote. So I'm checking, does it cross? Remember, my horizontal asymptote is y equals 3. So in order for my function to cross the horizontal asymptote, there has to be an x value that makes this y value equal to 3. So let's make 3 be g of x and see if I can solve for x. Again, it's a rational equation, so I'm going to multiply both sides by the denominator. That's going to, if I distribute, give me 3x squared plus 12x minus 15. And that's going to be equal to the numerator, 3x squared plus 2. Notice the 3x squareds will cancel. That's usually going to happen where the leading term kind of falls out. And I'm left with 12x minus 15 equals 2. If I add 15 and divide by 12, I get x equals 17 over 12. Okay? So I think that's my last slide, yeah. Go back. So with this information, and it's a lot of information, we can make a pretty rough sketch of what my graph is going to look like. It involves a little bit of deductive reasoning, a little bit of sort of logic and thinking. But the first thing we'll do in the video tomorrow is this exact example. So we'll start with this information that we found. I'll quickly run through how we found all this information again. And then we'll see if from that information, we can piece together what we know to get a rough sketch, a rough idea, a rough picture of what my graph for this rational function will actually look like. Okay, sometimes there is a little bit more work, but usually if you can find the intercepts and asymptotes, see if there's a removable discontinuity, and then check if it crosses, you have everything you need to draw a graph of a rational function. Okay, so it's been a long road, but we finally have analyzed this to the full extent that we can analyze it, and tomorrow we'll actually draw our first graph of a rational function.